Greetings. It is my honor and privilege to be presenting at the Biointerface 2022 conference. I'm sorry that I cannot be there in person, but I hope that this recorded presentation will be both informative and interesting, and I will be available to answer questions per the conference protocol at the conclusion of this presentation. My name is OGurel, and I serve as Chief Science Officer at Flight Material Sciences based in Montreal. And the topic for today's presentation will be immune dynamics at surfaces, an overview framework and applications, with the final part of the presentation focusing on nanotexturing. I can be reached at ogan.gurel@flight.tech. And I welcome connecting on LinkedIn if we haven't already on that platform. And if there's any kind of takeaway image from this presentation, it would be this super hydrophobic surface, which has lots of implications, of course, for medical technology, medical devices. And I'll be discussing this in more detail towards the latter part of the presentation. So the presentation will be in three parts. First, I'll be going through an overview of the immune system, and that will serve as a framework for dissecting some of the very complex issues involved. Secondly, I'll be talking about materials and surfaces, and finally, nanotexturing. Now, this is obviously a very complex subject, something that cannot be covered adequately or comprehensively in 15 minutes, but I'll really try to highlight the key points, the key results, and most importantly, some of the key implications that hopefully has relevance for your work. So a little bit of an overview of the immune system. We have a diverse audience, and I would like to just make sure we're on the same page when it comes to some of the immune concepts that will serve as the background for the framework that I'll present. So the immune system responds to injury or a pathogen. And of course, insertion of a device, a foreign body reaction, is a kind of injury. It may not have the same pejorative implications, but it's the same concept from a biological standpoint. So the immediate result is coagulation and vasoconstriction, and platelets serve a very important function in that. And then followed very soon after by vascular changes, vascular dilation, to allow cells to enter into that area. And those cells are recruited, and that begins the process of inflammation. And that inflammation progresses for several hours to days. Then that inflammation will resolve, and we shift to a repair process. So late inflammation will then go to a repair process that also involves other cells, macrophages, and fibroblasts. And we'll talk about the different cell populations that are involved in this. So the response to infection has two parts. There's innate immunity, as many of you are familiar with, and adaptive immunity, with innate immunity happening soon after the infection, and adaptive immunity, which is specific for certain pathogens, developing after that. So the epithelial barriers serve as part of the innate immunity, as well as macrophages, other phagocytes, dendritic cells, which we will talk about, NK cells, and complement. And this happens in a matter of minutes to hours. And then over the course of days, we have adaptive immunity, which has two parts, antibody-mediated immunity with B cells and cell-mediated immunity with T cells. Now, most of our discussion will actually talk about the innate immunity, because the innate immunity has a response that's general, not specific to a certain pathogen. And that type of general response is, of course, characteristic of the implantation of medical devices or other foreign bodies. This adaptive immunity is an open area, and I'll discuss a little bit of this later on, but this is a much more speculative and open area. So where does it fit in terms of a framework? So we have tissue injury, infection, and regeneration repair, as I indicated, as two major processes. And then we have the innate immune system and the adaptive immune system. We have inflammation early on leading to repair. And so biomaterial properties, as they interact with the immune system, will interact with these specific elements, as opposed to the immune system as some amorphous generic entity. We talk about the innate, the adaptive, inflammation, repair, and of course, the different cells that are involved in that. And the biomaterial properties that I'll be focusing are those, the origin, the type of material, chemical modifications on the surfaces, and then very importantly, the physical properties, the size, the dimensions on the surfaces, the hydrophobicity, the charge, and importantly, the surface texture, which we will be emphasizing the latter part of the presentation. Now, these are not mutually exclusive. The surface texture has certain size dimensions, certain hydrophobicity, but I tease these dimensions out for the sake of discussion. Now, what you'll not notice here is biomaterial properties with embedded or impregnated biologics. This is a separate area, so I'm mostly focusing on the physical chemical properties of the surface insofar as it influences the immune dynamics. Remember that I mentioned that the adaptive immune system is still an open area, and some of those biologics will influence more this adaptive immune system. But when it comes to the innate, as well as inflammation and repair, some physical properties definitely do influence these processes, and that's what I will focus on. So I'll talk about some material and surface properties. So we'll focus first on the origin. Now, about 45% of medical devices implanted are polymers. So we have synthetic or natural polymers, and these each have advantages and disadvantages, respectively. So one of the aspects of the disadvantages is that the synthetic, which are a large number of medical devices, of course, incite a vigorous high immune response. The second thing we'll talk about are chemical moieties. And so we have different groups and their surfaces, their charges, focal adhesions, ability to assess fibronectin domains, inflammatory cell infiltration, macrophage response. So we start with amino groups, which are generally positively charged and hydrophilic, hydroxyl groups, which are also hydrophilic and neutral, carboxyl groups, which are hydrophilic and negative, and methyl groups, which are hydrophobic and neutral. And these are typical chemical moieties that might be added to a surface, to a polymer, to influence these properties. So let's look at a little bit how these interact with the immune system. So amino groups tend to be anti-inflammatory, and they influence cell differentiation pathways in a medium fashion, such as osteoblasts for osseointegration, and they have relatively high bioactivity. In contrast are the hydrophobic methyl groups, or groups like methyl groups, which have a neutral charge, of course, have a very high, relatively high inflammatory cell infiltration, but low ability to influence cell differentiation, as in osteoblasts and osseointegration. But you can see there's no definite pattern. The carboxyl groups, the negative charge, tend to have a low inflammatory, but they can have a medium ability for fibronectin domains. So it's really a mixture. There's no pattern related to chemical moiety. So it's a very complex to really predict through chemical modification what are going to be the results of interaction with the immune system. So another parameter, which is very interesting, is physical size of the topography of the surface. So as I mentioned, these are the frameworks, and so we'll talk about the mesoscale. The mesoscale tends to influence macrophages. These are larger particles, and they stimulate the repair process. Then we have the micron scale. Also, macrophages tend to be influenced there, and the submicron scale. So macrophages are particularly influenced by this size dimension. And then on the nanoscale, we have platelets being influenced. Platelets are obviously very small and involved in the coagulation. So that type of thrombotic influence can be influenced by nanoscale surfacing. Macrophages as well, and dendritic cells, which are involved in the innate immune response. So one of the interesting things is that the dendritic cells also related to the repair process. And All of these dimensions are relatively anti-inflammatory, but the dendritic cells also have a pro-inflammatory, and the platelets, of course, related to thrombosis. So one of the takeaways from this is that the nanoscale has a lot more possibilities for immune modulation than the mesomicron or submicron scale. And we'll talk about the implications of this shortly. Now, what about shape? For example, particles or the topography, the shape, is it spherical? Is it elongated? Um, Macrophages can be influenced more by longer rods, pentagonal, triangular objects. Smooth surfaces cause a less acute reaction than rough, sharp corners and acute angled surfaces. Neutrophils are also influenced more by rough surfaces, and dendritic cells are rod-shaped particles. So the takeaway message here is that in general, rougher, more complex surfaces led to more biological effects. So if we can summarize in terms of the immune dynamics, we have the biomaterial properties. Synthetic materials tend to be more pro-inflammatory than natural. This can be considered a significant disadvantage. On the chemical side, amino groups tend to have a high bioactivity. Hydrophobic methyl groups tend to have low bioactivity, but there's no systematic pattern. If we look at the size, meso to nanoscale particles generally act on macrophages. Some mesoscale properties can stimulate repair processes. These are generally anti-inflammatory, but the more interesting and more diverse properties emerge from nanoscale particles and surfaces. They act on a more diverse range of cells, including platelets and dendritic cells, and they can be pro-inflammatory as well as pro-repair effects. And more complex surfaces tend to have more biological effects. So on the adaptive side, as I mentioned, we don't have a lot of physical mechanisms that influence that. That's a much more biological process that the B cells and T cells, as we described. That's a topic perhaps for another presentation. So in conclusion, we should use synthetic materials, non-chemical modification, nanoscale surfaces, and complex surfaces. And this leads to the topic of nanotexturing, which I'll go over quickly. And that's the special expertise of Flight. So this is an example of untreated steel. Temporary coatings can flake off, they can delaminate, they can be toxic. We take lasers and we create nanotextured surfaces. And this is an example of water-repelling peaks. And you saw that image, we'll see it later, where we have that super hydrophobic surfaces. So coatings, as well as chemical modifications, have significant disadvantage, particularly in medical devices. They can leave toxic traces, unknown effects, regulatory hurdles, extra costs, and patient complications. So Flight's treatment is not a coating, as we mentioned. It is a treatment, a nanotexturing. So we're not adding material, we're not removing material, and we're not an additive. So this can be applied to all sorts of devices, creating hydrophobic surface, hydrophilic surfaces, oleophilic, oleophobic, omniphobic, and custom surfaces. And what's really intriguing is the possibility of having multi-scale nanotexturing that can be anti-inflammatory, pro-repair, and really matching the complexity of the immune system. So this is an example of that super hydrophobic surface. So we have examples from the research, of course, of improving tissue compatibility with these types of surfaces, enhancing endothelialization. Remember, attracting these cells. As we pointed out, the nanotexturing seems to have more diverse and impactful effects on cells. So in coronary stents, and then antimicrobial cells, surfaces in this COVID era. So this can, it's not technically an immune effect, but it can prevent bacteria from binding. So surface micropattern limits bacterial contamination. On the cardiovascular side, preventing restenosis and thrombosis. We talked about the platelet effect as well. So reduce platelet adhesion. And in order to achieve that, because of the small size of platelets, you really need something on the nanoscale. And finally, on the dental and ortho side, osseointegration, integrating into the bone, and of course, interacting with osteoblasts, which drive that process in a cellular fashion, as well as preventing infection. So we have those issues with dental as well as orthopedic. And these are some results, adhesion and bone growth around implanted laser groove functionalized pins. So I think my time is up. I'm happy to answer any questions. Thank you very much. As we say in Canada, or I should say in Montreal, merci beaucoup. And if we don't have the chance to answer your questions during our short discussion period now, I can always be reached at ogan.gurel@flight.tech. And of course, welcome connecting on LinkedIn. And here's our website as well. Thank you very much, and look forward to the questions.